Hello, this is 1.1 functions. This is actually, to tell you the truth, the beginning of this course. The F section is kind of more of a review type sections, and so 1.1 functions is really what I would call the beginning of this course. So, and we begin this course with basically functions, and we will have in this one, I believe, 5 or 6 videos from this section, and there will be 2 parts on the overview. If you notice, this is overview part 1. So as you can tell, whenever there's 2 or more overviews, means the section is really long. That doesn't mean that it's really hard. It just means there's a lot to cover in that section. So but anyway, this is overview part 1. And we begin with the definition of what a relation is. And what a relation is the correspondence between 2 sets. And you're like, well, what's a set? Well, a set is a list of elements. So you have this container over here that has a lot of elements in it. And it could be numbers, which we're in a math class, they're usually numbers in a math course. Okay? But it doesn't have to be numbers, but it could be just a set of items. But like I said, this is a math course, so those items are usually numbers. And then you have another set over here, and it's the same thing. And so you take a correspondence between an element from this set to an element of this set, and you make a listing. And that listing is actually the relation. So the relation is that correspondence between 2 sets. So let me show you what I'm talking about. So you have 2 sets of items. And like I said, you can have, they're usually numbers. So let's say 1, 2, 3, 4. And so they can have more than that number of elements. You could have a lot of elements in that set. And over here, there are 3 elements. And we'll call those 7, 8, and 9. So we have a correspondence. So what a correspondence would look like is this. 1 might go to 7. 2 corresponds to 8. 3 corresponds to 9. You're like, well, wait a minute, what does 4 correspond to? Well, it could correspond to the same element of another one. So it doesn't have to go to a different number to be a relation. As a matter of fact, to be a relation, that 4 could actually go to another number as well. So that's a relation. A relation is a correspondence. And the way to write a relation, this is what we call a mapping. And this is a way to write a relation. But another way to write a relation is more commonly called ordered pairs. So what you do is you make a listing of what these 2 sets are called. And I like calling this set D, and you'll know why later. And this one's set R. And some of you guys are already, I know what it means. I know what it means. Okay, yeah. You probably know why this set's called D, and why this set is called R. And again, it has something to do with the idea of functions, which we'll talk about in a bit. So this relation here, and I'm going to call this relation A, is a set of ordered pairs. Well, ordered pairs has 2 coordinates. A 1 in this case will go to 7. A 2 will go to 8. A 3 will go to 9. A 4 will go to 9. And a 4 will go to 10. So that is a relation. And in that relation, there are 1, 2, 3, 4, 5 relationships. So there are basically 5 ordered pairs. Now let's take the ordered pair. Okay, let's take any ordered pair. What does the diagram of an ordered pair look like? Well, if you take the 1, 7 for example, the 1 has a special name, and it's called the abscissa. And I think we talked about this back in F, and this one is called the ordinate. So we had talked about this prior to this. Some people just simply call it the x coordinate, and the ordinate simply the y coordinate. So again, we discussed this in the previous section here. Actually, it's F3, I believe. So the abscissa and the ordinate. Now, so when we have, that's what a relation is. It's just a set of ordered pairs. That's what I usually call it. I don't call it really a it's a combination between two sets. It's that connection. I just call it a set of ordered pairs, because when you have a set of ordered pairs, obviously 1 relates to 7, 2 relates to 8, and 3 relates to 9, and so on. Okay, but this is what makes a relation. It's just a set of ordered pairs. Okay, now a function is a special type of relation. So let me explain what a function is. All right, a function. What is the definition? Well, a definition of a function is a relation where the input, but remember, input is called the abscissa. This is what's on that first one. So the abscissa corresponds to only one ordinate, and that's what we'd call an output. Well, I actually got this built backwards. Only one output, and that's called the ordinate. I guess it doesn't matter how you write it out, I don't believe. So output, ordinate, same thing. So what a function is, for each input, there is one output. I relate a function like a Coke machine. When you put money into a Coke machine, and then put your money in, hit a selection, and then one item comes out. Okay, so a function is like a Coke machine. When I was in high school, I played football, and we had a Coke machine. It was, back in those days, it was like 35 cents. And we would put 35 cents in this machine and push a button. And if that it was a Pepsi, you get your Pepsi. But then you wait about 2 seconds, and then you get another Pepsi. And then you get another Pepsi. And then 35 cents would empty that whole machine out. We loved that machine. Coaches didn't take too long to figure that out, what happened when they opened it up and they got 35 cents out, and then all the Cokes were gone. Well, Pepsis were gone. So, but that was not a function, because the reason it wasn't a function is because we put money in and we got multiple outputs. Not a function. Okay, to be a function, one thing in gives me one thing out. So the notation of a function is f, because it's most commonly it's called f, and this is x. Now, why it's called f of x? You don't read this as f times x. A lot of people think of this as a multiplication. It's not a multiplication. This is basically the name of the machine. Okay, this reads f of x, and what that's basically saying is the name of the machine is f, and the input is given out is the x. So the x is the input. So remember I mentioned the Pepsi machine? Well, this is what a function notation would be for the Pepsi machine. Pepsi is the name of the machine, and what does it take? Well, it doesn't take x's, it doesn't take numbers, it takes money. So a Pepsi function, if you will, would be a Pepsi, comma, $. You don't read it as Pepsi times $. You read it as Pepsi. What does it take? It takes money. So this is the function f of x. So what's the name of the machine? F. What is it's taking? The inputs. So if it's a function and you have a set of ordered pairs, let's say an ordered pair in this function, because remember, a function is just a relation. Let's say one input is 2, 3. That's a one ordered pair of that relation. So how would you write that? Well, as a function notation, you would say f of what? What is the x? The x is 2. What is the output? The output is 3. So f of 2 equals 3. 2 is the input, 3 is the output. So that's the first notation of what you call evaluating a function. And I got that down here. Example of an evaluate. That's an example of an evaluate. So f of 2 equals 3. And sometimes the machine is given to you in a certain way. Sometimes it's given to you in an equation format. And we will talk about that in a bit. So, but look back at set A. Is set A a relation? You betcha. It's a set of ordered pairs. But is it a function? So I guess the question becomes, is every relation a function? Okay? Every function is a relation by definition, because that's what a function is. A function is a relation, blah, blah, blah. But is every relation a function? Well, look at set A. Set A is a relation because it's a set of ordered pairs. 1 gives me 7, 2 gives me 8, 3 gives me 9, 4 gives me 9, and 4 gives me 10. Where does the problem occur? The 4 gives me the 4 gives me two different numbers. The 4 gives me a 9 and the 4 gives me a 10. That input is twice. So when you're looking at ordered pairs, if you want to know whether it's a function or not, what you do is you go through the list, go through the relation, determine if there's any repeated x coordinates. And there is. 4 and a 4. Now if you take this off right here and you lose that number, 410, so you take that ordered pair away. Now look at set A. Set A is 1, 7, 2, 8, 3, 9, and 4, 9. You say, whoops, still not a function because the 9 is repeated. Oh no. I didn't say the output can't be repeated. I mean, think about the Pepsi machine. If I put my money in and get a Pepsi, one Pepsi comes out. You come later, put your money in, different money, different amounts. So you put your money in and you push a button, Pepsi can come out. So we could get the same output, but our money was different. So 3 can give me 9 and 4 can give me 9. So outputs can be repeated. Inputs cannot to be a function. But it doesn't matter what to be a relation. So all a relation requires is this: if you have a list of ordered pairs. So you have to have that correspondence between two sets. And that's what ordered pairs are. Ordered pairs are just the correspondence between two sets. You take the elements of one set and take the elements of the other set and you match one to another. And when you make that matching, you create the ordered pairs. Those ordered pairs in itself is the relation. So the next question becomes, is that relation a function? Well, then you go and look at the set of ordered pairs. Now, when we get to some next the videos that are coming up, we're going to go into a little bit more detail of what is a function and what is not a function. Some of them will be just ordered pairs, but some of them will be in equation format. Some will be in a mapping format. So in a mapping, you can probably pretty much guess. And a mapping is to be a function. You can't have anything going to two different things over here. So if you have a branch over here twice, if you have branching off to 9 and 4 branching off to some other number, then it's not going to be a function. So, but 2 branches off of one number over here is okay, because that's an output. So it all depends on where the arrows are pointing. Okay. So now you could probably tell me why I call this D and why I call this R. Because look at this part. The first set of elements that you're putting as inputs, that is called the domain. And the other set that the outputs, the ordinates, is the range. So you remember I said alpha 2 equals 3 on that one specific ordered pair. 2 was an input because that was put into the function. Alpha 2 was put in. And what came out of that was 3. And so that's an output. So inputs give me is what's put into the machine, and 3 is what comes out. So let's say alpha. So if you have alpha 2 equals 3, okay. Now, like I said, 2 is an input, but 3 is an output. Is there a way to remember that? And I have these weird ways to remember things, but it works for me. Maybe I'm a weird person, but I can remember how to do things certain ways. Domain, the letter D, comes before the R in the word range. The I in the word input comes before the word O in output. So you match these and you match those. I know it sounds weird and it's not mathematically formal, but I learned math, like I said in the previous video. I'm a very informal, formal learner, and so I have to read things and put it in my own language. And it works for some people, and other people like the formality of it all. And but I becomes before O, D comes before R, and that's how I remember it. Okay, if you remember abscissa, okay, abscissa and the ordinate, abscissa, A comes before the word O, the letter O in the word ordinate. So it's all, to me, it all kind of blocks off together. So abscissas, inputs, and domains all comes before these letters in the range R, output O, and ordinate O. So, and if it doesn't work for you, that's fine. You just have to memorize it your own way. So, but anyway, so the domain is a set of X, or the inputs, called the independent variables. So the inputs are called the independent variables. Why is it called independent variables? Because what is inputted into the function depends on what you want to put in. But what comes out depends on what you put in. So the dependent variable, okay, so is over here. So in other words, look at this mapping. Which one do I go first? Do I put 1 in, 2, 3, or 4? Yeah, well, you can put any of them in. That's why it's called independent. But how am I going to get 8? How am I going to get 8? I'm going to get 8 if I put 2 in. So if I want my output to be 8, I had to put 2 in to get that 8 according to this mapping. So if I want 8 in my hands as an output, okay, then I had to put a 2 into the function. That's why the 8 would be a dependent variable, and it depended on what you put in, and 2 was put in because that was the independent variable. Okay, so it's like on a Pepsi machine. You know, what if I wanted to put, if I wanted to get Pepsi, if I wanted to get a Pepsi, well, you better not push the button that says Mountain Dew. So if I wanted that Pepsi output, you can't just blindly go through there and push any button you want to. You actually have to push a specific button on that machine. So the Pepsi is the dependent variable. The independent would be the money and the pushing the correct button. So that's kind of how that works. And I've already given an example of how to evaluate. And now how to determine whether the relation is a function. So here is as ordered pairs, as mappings, and as equations. I've given this first two to you. Remember, as ordered pairs, the x coordinate cannot be repeated to be a function. A mapping can only branch to one element at a time. So this mapping that's up here now is a function. But if I put a 4 and put another number down here like 10 and have 4 going to 10 as well, 4 is repeated and then it would not be a function. So mapping's got to have one branch coming off of each one of these numbers over here, not 2 branches. Ordered pairs can be functions if there is no repeated x coordinate or abscissa. But what about the other one, the equations? Well, that's a little different, and those are probably about the most difficult to determine whether they're functions, but there's little rules that you can actually follow. If I had x plus y equals 6, now that is a function. Because if I put in x in, let's say x was 2, then the output would have to be 4, because 2 plus 4 is 6. If I put in 3, then the output has to be 3. Okay, so that's function. Now, what a lot of people will try to do is that when they have an equation, is they'll solve for y. Now, why do they solve for y? Because y is f of x. So remember I said the notation is f of x for a function, and I said f of 2 gives me the 3. Well, 3 is the y coordinate. So y equals f of x. So remember, x was 2 and y was 3. So y is f of x. So you're like, okay, then why is this such a big deal how to do this? Well, if y is f of x and you solve this equation for y, and you get an equation out of that has no plus or minuses. You cannot have a plus or minus in that, because if you have a plus or minus, then you put a number in for the x, you'll get a plus that number and a minus that number. Now, this one won't cause a problem, because when you subtract x, you have y equals 6 minus x. Now, here, if you put a number in for the x, like 3 or 2 or 5, you get one answer. So that's not a problem. But look at this one. x plus y squared equals 6. Now, if you put a number in here, let's say this one, you put a number in for x, you'll get 0 or whatever, put 0 in or 1 in or whatever you want to put in, and then move it over here and then take the square root of it, you get the plus or minus. So here's the equation. This is how you write the equation. Y squared equals 6 minus x. I'm doing exactly the same thing here. And then take the square root of both sides. But when you take the square root, there's something called the square root property, and then you got to tack on a plus or minus. So this one right here can be written in function notation because it is a function. But this is not a function. Because when you put a number in, let's say you put 2 into this one. 6 minus 2. So 2 is put in. 6 minus 2 is 4. And the square root of 4 is 2. But there's a plus or minus on the outside, so it's plus or minus 2. So the answers are 2, comma 2, and 2, comma negative 2. So x is 2. I have 2 outputs. So you're like, well, I can skim all over that, can't I? Can I just say, well, if I see a square on the y, you betcha that's what you look for. So if you see a square on any y coordinate, you can automatically say, well, when I solve for y, it's going to be a plus or minus. So that's kind of what you look for. You look for y squares, and those are not going to be functions. Now that's not a hard fast rule for everything. And if you ever get into a bind and you're like, okay, is it or is it not? Put a number in front of the x, solve for y, and if you get one answer, then you're in business. But if you immediately get 2 answers, then you got a problem. Because there's not all of them are that way. For example, I can give one like this: x plus the absolute value of y equals 6. So absolute value of y equals 6 minus x. Put a number in there. So put an x equals 2 in that one. You'll have, if x is 2, then it would be 6 minus 2, which is 4. And the absolute value of absolute value of y equals 4. Well, absolute value of what numbers is 4? You just have 4, of course. Yeah, that's true. But also, negative 4 would be put in and it would satisfy too. So 4 is put in here, or negative 4. It's 2 outputs though. So putting in 2 in for the x gave me 2 possibilities for the y. So this is one thing that doesn't have a square in the y, but yeah, okay, then there's an absolute value. There's an absolute value around the y. That's true, but there's a lot of these little rules you got to remember that. So there's just 2 of them. So you have y squares. If you have a square around the y, not a function. Absolute value around the y's, not a function. Okay, so that's going to be your job to figure that out. Now, there's too many rules to sit here and tell you every one of the rules. So sometimes you just have to put a number in front of the x, solve for the y, and see what happens. So a lot of the times, though, is these little rules that you can look at. Okay, that's what it is. But you're going to forget them. You don't remember everything you learn. You forget some things, but the thing is, you fall back on some basic things when you forget those things. And that's putting numbers in and try to solve it. So if you learn that in math after a while, I mean, I don't remember everything I've been exposed to in math, but I have the knowledge of going back to a more basic thing and work my way through it. And then if you do that enough times, you'll remember the rules because you don't have to do that every time. But you got to stay in math a long time for that. So, but sometimes you just have to kind of flow through it. So, all right, this is the end of the overview part 1. Coming up is part 2, and thank you for watching.